All right, so we're starting with number 15, which is the one where the crew member is standing on a scale in a ship, and the Y for it is a force diagram. Question we're asked about though, what does a scale measure? What force? Normal force. So whatever they say on the scale reading was, they're telling you what the normal force was. So my force diagram, come on, what's going on? Excuse me for a second, I don't know why. Alright, let's try this again. So 15. So I've got my scale. And my person saying, I remember if you can't draw as well as I don't, you don't worry about it. You know, I had to give lessons, tutoring on it. And I'm going to have a weight of my person down on the scale. The scale is going to push back up with a normal force. And then kind of the tricky one is sometimes I'll have an acceleration up, but other times I'm going to have an acceleration down, and other times I might even have a zero acceleration, because I'm going through a bunch of different scenarios here, right? You know, it's calm water, which would be no acceleration, and then up and down. So they want to know the maximum upwards acceleration experience and the maximum downwards by the person. So, here, and that probably would suffice for a diagram. Alright, so now, grab an equation from our equation sheet, and we're dealing with net force causing acceleration. So the one I'm going to grab my mouse, if the board is acting up, is this one right here. Paste that in. Oh, come on. Let me do it again. Alright, so my notebook decided to crash again. Yay. Alright. So we're going to use the same equation the whole time. And for acceleration 0, so we have two forces. We have normal force up, and since we said up is positive, that's always going to be a positive term. And we have the weight down, so that's always going to be a negative term. So for all of my sum of my forces, I'm going to put in, and this we're doing in red, force normal plus a negative force of gravity, and then over my mass. I don't think they tell me my mass, if I remember correctly. Nope, they don't. That's okay. This first part's going to help us find that mass. Over, we'll say I have a mass of m, and in this case, that equals 0. Right? So I actually need one other equation for my equation sheet, and it's back from earlier. Let's see where we are. Right back up here. And it's that force of gravity. Why do I do that every time? So we also need this up here. And so I've kind of jammed myself up here layout-wise. So now, skipping a little bit of algebra, I can say the normal force equals the force of gravity, which is mg, right? And they tell me my normal force in this case, 760 newtons for me. It's going to be different for you. So I've got 760 newtons equals whatever my mass is, and since this takes place on the Earth, I'm going to say 9.81 newtons per kilogram. And if I pull out my calculator, and you kind of say, okay, that doesn't help answer either one. It's going to be crucial to know this mass to be able to answer either of these two other questions. So I get m equals 77.47196738 kilograms. And I'm going to keep it all on my calculator because I don't want to make rounding errors. So now when is everyone good with that? Okay. Now, that acceleration up, and because it's up, I know the net force is up. Therefore, it's going to be the largest normal force. All right? Because that's the only way I can produce an upward force. So I'm going to use the same thing. I'll try to write a little bit smaller now. Force normal plus a negative force of gravity all over m equals a. And grabbing my largest one for me is 930. So force normal is 930 newtons. It's positive minus, I know my weight, 760 newtons over my 77.47196738 kilograms equals A. And it's going to be positive, which is great. So that means it's upward, which is what we want. And then we can keep going and do the exact same thing for the downwards one, except this time it's my minimum normal force, which for me is 570. So 570 newtons minus 760 newtons over 77.47196738 kilograms equals A. Am I going to get a positive or negative A? negative, which, yay, that's what I wanted, because the acceleration needs to be down. All right? Make sure you pay attention. I don't remember. See, I'm not sure if they want a positive or a negative value in here. So, if you get this one wrong the first time and you didn't put negative, maybe they wanted negative. All right? All right, on to number 5, where you have a jet landing and traveling due south. It comes to rest in this, and they want to know what's its acceleration. There's a number that's implied in the text that isn't given to us, and that's the final velocity. What's the final velocity of the jet? 0, because that's what it means to be at rest, right? So they don't say, you know, it gets to a velocity of 0, but we know that from the context. So I'm going to put in some text here. Let's see. Text tool. Reduce the speed, the acceleration and the velocity must be in opposite direction. The velocity must be in opposite directions. The longer the distance it takes to stop, the less acceleration needed. Actually, I think that would probably do it. Probably all you would need is you're recognizing how you're going to solve for the direction of the acceleration, and you're also recognizing what connection that has to the direction of the velocity. All right, and those are the 2 parts it wants you to hone in on. I hope I'm recording. Okay. Now you could do a diagram and everything else. I'm not. So now I need to look for an equation that helps me relate velocity, changes in velocity and acceleration and distance. And the one I'm looking for is this one right here, so I'm going to grab that. And put that in here. So I'm starting with my value equation. The most common mistake using this equation is to mess up the, and forget the squared terms in it. Just like in the big, long kinematics ones, that's the most common mistake also. So, I know my final velocity is at 0. My initial for me was 83.8 meters per second, and it comes to rest in 943 meters. I'm going south, so as I said in my y, my acceleration must be opposite. Which way should we call positive? To the north or to the south? It's up to you guys. North? Okay, so we'll call to the north positive. That means my velocity is negative 83.8 meters per second because it's to the south. I'm expecting a positive acceleration, and this 943 meters is going to be negative also because it's pointing down, moving south. All right, so that's fine. So we're calling to the north positive, and so my V final is 0, 0. That would be squared. My V initial is negative 83.3 meters per second squared plus 2, I don't know A, but this is negative, and of course I forgot what my number was, 943 meters. And solve for A. And I should get a positive number because that's going to be positive because it's squared. That, when I move to the other side, will be positive. And yay, it's going to point towards the north, which is what I predicted. So, that is number 5. All right, on to 14. Now, in 14, our Y is a force diagram and other concepts. So not only do we need to make sure we have a good force diagram in there, we need to also explain a little more what's going on. And part of that comes into the fact that we're looking for the force that produces this acceleration in him. So we need to explain that things like, well, let's see. I think I'll first write my explanation. The idea is that net force produces acceleration. Is he coming out of blocks? The sprinter pushes on the blocks, so since forces come in pairs, the blocks push back on the sprinter, providing the net force. So that's why this one was force diagram and other concepts, because you needed to recognize that second part for other part. Yeah. We're on 14. Sorry, yeah, I should have put that up here. All right, so let's see. Let's draw. Here's the ground. Those are the blocks. Now to use my artistic ability. That's the sprinter. Give him a head. How about that? That's my other face. So, sprinter is going to accelerate this way. Notice my acceleration does not touch my object, right? There are a couple other forces going on here, like the sprinter's on the Earth, so it must have force of gravity, therefore has a normal force. We don't really care too much about those. What we care about is this force on the sprinter from the blocks. Not because that's the one that's going to be pointing in the direction of acceleration, providing the net force. There is, now I wouldn't draw it in here, I'm just going to draw it in a dotted line here. There would be a force backwards like that of the sprinter on the block. But that one's not affecting the sprinter, that one's actually affecting the Earth, or the blocks. How many people are runners in here? Very many? What if someone doesn't stand on your blocks? What happens? They move, but if they stand on them, they're nice and steady, right? Because if the blocks aren't tied to the Earth, they don't have much inertia. They just go backwards and you slip. But if you have someone stand on them, now they're tied to the Earth or tied to that person, and you can push on them. That's why you always get like the throwers to stand on your blocks, because then there's no way they're moving. You know, you get a distance runner, and Forget about it. So that would be the Y. You would need both parts there. Good on that? You guys are too talkative today. I tell you. All right, so now this reminds what we're looking for. We have the acceleration. We have the mass, and we want to know the net force on it. We already figured out the second part through our Y. So we're going to go here, and we're looking for that relationship again between net force, inertia, and acceleration, which is right here. All right. And so we're looking for the net force this time. Oops, I'm still in dotted line. So we're looking for that total force. We have the mass. We have the acceleration. Excuse me. Meters per second. And now just solve. Right? Yay! All right, so we're going to go over 17, which we have the power output of a 1.1 G flat. What's that G stand for? Grams. Should we keep the mass in grams? No, we should put it in kilograms. And walk straight up the window pane at this centimeters per second. Ooh, we got to convert that to meters per second. And because they tell us it's moving at that constant speed, I know it's not accelerating. It's one of those kind of hidden things in there. All right? And that's exactly why this one is, again, a diagram and an explanation. So for the diagram, here's the fly. The weight will be down. The force on them from the wall will be up, and the acceleration is 0. I know I'm talking fast because I don't want to run out of time. And so we're going to use that fact. We know, like from doing the boat one, that when this happens, the weight of the fly equals the force on it from the wall, right? And what's happening is that force, it's not a net force. There's no net force on here. And that's why we have to incorporate that the work done on the fly is giving it PE grab, and the faster it is done, the more power needed. The force of the wall does the work on the fly. It's probably good. So, I'm going to start off. I think I have yay. That, and I'm also going to need, though, my power equation. And in reality, I'm going to use that last form of it. So I'm going to forget about this part and forget about that part and use the force and the velocity. So the force on my fly here, I have force of the wall up plus negative mg, the weight of the fly, over m equals 0. Therefore, the force of the wall equals the mass of the fly times the gravitational field strength. I'm skipping one equation, right? Remember, I'm going to flip back to the first one if you're not sure. So then I can go into power here. Power equals that force, which would be the force of the wall, and the velocity of the fly. So this would be mg times the velocity given to me. Make sure that you convert the mass to kilograms before you put it in. Make sure you convert that velocity to meters per second before you put it in. They won't offset each other. You'll end up with a very wrong answer. All right, I will post these notes. Sorry the last one got rushed.